Yeah. So welcome to another session of analog microelectronic circuits, and so far we discussed the uh, almost some of the negative feedback applications of Opamp, starting from amplifiers, difference amplifier, instrumentation amplifier, and in yesterday's class we discussed about even precision rectifiers. Right. So in all these cases we saw that there is a valid negative feedback exists in the circuit, and for that reason we made all analysis based on the virtual short property, right? So virtual short property, as we discussed, we know that virtual short or virtual ground, we can say that a point is virtually short or virtual ground when it has a zero voltage and when it draws no current, in contrast with a physical short where a physical ground or a ordinary ground can actually draw infinite current, but a virtual ground draws no current. That is what we have discussed about op-amps. Now the property of virtual ground or virtual short is applicable only when we use an op-amp in a negative feedback configuration. For the reason of what I stated here is I can always write V out as A into V2 minus V1, and when A tends to infinity, the difference voltage V2 minus V1 will tend to 0 only when your V out is finite. And V out is finite only when you use an op-amp in a negative feedback mode, in both positive feedback and when you use an op-amp in a open loop mode, your output tend to grow. And because of power supply limitation, output is getting saturated at plus Vz and minus Vz, and in both cases we are not considering output voltage as a finite quantity. Therefore, we cannot use the concept of virtual short or virtual ground whenever op-amp is configured in a configured in a positive feedback or in a open loop configuration, right? So having said that, I'm just moving to the open loop applications of op-amp. So far what we considered all are negative feedback closed loop applications. Let me start with open loop configuration of op-amp. In that, the very first thing what we discuss will be a basic comparator. Alright. So when we talk about comparator, so a comparator, as the name suggests, it basically compares a voltage on one of the input of an op-amp with another voltage on the other input of the op-amp. So so far we know that we generally mark op-amp as say plus and minus two input terminals, right, with power supply given to this. Now the moment we configure this op-amp as a comparator, what we do is we connect a signal voltage. Say we connect a signal voltage to one input. Say I am connecting this signal voltage as V signal, and to the other input, so we have two input terminals, right? To the other input I'll be connecting a known voltage or a reference voltage. Say I have reference voltage as Vref, and what I want or what I'm expecting at the output is the signal voltage or the voltage which I have applied to one of the input terminal will be compared with the known voltage or the reference voltage, and based on that op-amp will actually make a decision. What decision op-amp will make? Op-amp will make a decision that whether this input voltage is the signal voltage is greater than threshold or less than threshold. Right. That is what generally a comparator does. So we can say that two voltages at the input side, where this is an analog voltage, and the output what we get will be whether the input voltage is greater than this threshold or less than this threshold, right? And since we are using this in open loop configuration, so let me write, I am assuming that the open loop gain is infinity, and since I am using it in open loop configuration, in this case V out will be either plus Vsat or minus Vsat. V out will be V out will go to the plus extreme, that again it is limited by the power supply, and minus extreme again limited by the power supply. Now why are we writing as plus Vz and minus Vz? Because what I am considering is a dual supply op-amp where I connect plus VCC and minus VE, which works on dual power supply. That is why we write output as plus Vsat and minus Vsat. Alright. Now, so comparator can be also considered as a what is a single bit converter, analog to digital converter, right? So when you have a signal, it is compared with the reference and a decision is made, and the decision is either high or low. So when if it is high, we can say that the input signal is greater than the reference voltage. If it is low, we can say that the input voltage is lesser than the threshold, or lesser than the reference voltage. Now, since we can operate Opamp in two modes, inverting and non-inverting, we can have an inverting comparator and a non-inverting comparator. Two versions are possible, right? And there are numerous applications where we need to compare voltage, compare signals and make a decision. And this is the simplest form. We have there are many sophisticated circuits which need highly precise comparators, especially in all the data converter applications we go for comparators. But now what we discuss here will be generally used for all the discrete applications, right? So we are looking for an output which can go either to plus Vset or to minus Vset, right? So now by looking at the configuration, or by looking at the circuit what I have drawn now, can you tell me what type of comparator this is? Can I get a response in the chat window? So how will you decide that? See, your output voltage, I can say that your output voltage will be either plus Vsat or minus Vsat. Output will be plus Vsat if when your V signal is greater than Vref, output will be plus Vsat, and if your V signal is less than Vref, output will be minus Vsat. Yeah, so when you say negative comparator, yeah, generally how we give the nomenclature here is, since the input signal is given to the positive input terminal, you look at the expression for the output. When your signal is greater than reference, output is plus Vsat. Signal is less than reference, output is minus Vsat, and for that reason we call this as a non-inverting comparator. Signal is high, output is also high. If the signal is low or lesser than the reference, output is also lesser or low. For that reason we call it as a non-inverting comparator, not negative comparator. The terminology what we use is non-inverting comparator, right? So the output voltage changes from one saturation level to another saturation level at what is the point when? So the switching point will be, let us look at this. Let me draw the input signal here. This is the input signal. Say input signal, this is peak, this is say Vm, and this is minus Vm. Now I have given a reference, and you can see that the reference voltage what I have given is a positive reference, plus Vref. The plus of the battery is connected to the negative, and just for an example sake, let me take this equal to 1 volt, where your signal peak is somewhere equal to 5. I'll assume that this is 5 volt, this is minus 5 volt, and I have a reference voltage, and reference voltage value is equal to say 1 volt. This is 1 volt, which is the reference, right? So how will this respond, or how can we say that? How do we draw the output for this circuit? Look at this. Yeah. So how does this respond? Let me mark few points. The input signal starts here. Right. So the comparison also starts here. You have an Opamp here. Sorry, you have an Opamp here. And now these two voltages will be compared and an output will be produced. Now what is the output? So how can I write the output voltage expression here? Output voltage can be written as your Vout will be always V out can be written as A times V signal minus V ref, or in turn I'll write it as, this is a V2, this is V1. That is what we have written so far. So I can write it as V out is equal to A times V2 minus V1, right? Now, if the difference voltage, if V2 minus V1, if the difference voltage, if it is positive, output will be that voltage multiplied by A. Assuming A as infinity, output will also go to infinity, but it will be limited at plus Vsat. Now, if the difference voltage is negative, output will actually go to minus Vsat. That is what, that is how we should understand, right? So now look at this case and let me know how we can draw the output waveform. Now look at this range. Look at this range. From here, from 0 till this point, which terminal is having a higher voltage? This can be considered as 0. This is 0 volt. Now from 0 till, from 0, look at the input voltage. Yeah, input voltage is actually increasing, but from 0 till this point, reference is high. When you say reference is high, which terminal is having higher voltage? Reference is connected to minus. Minus is having a higher voltage, so the difference voltage will be negative. If it is negative, output will actually go to minus Vsat. Alright, so how it will start? Yeah, so we have a very small portion here. Let me mark it. Right, so output will start from minus Vsat. So let me consider this as plus Vsat and this as minus Vsat. So output will start from minus Vsat. Now what will happen? At this specific point, your Vref and input signal both are equal, and soon after that, now you can see that input voltage is actually slightly getting positive. So this point can be considered as a point where the switching happens, right? So till that point it is negative, but what happens when exactly both are equal? When both are equal, the difference is 0, right? So from negative Vsat, the output will tend to rise high, but quickly we will see that the positive input terminal is increasing further. It is increasing further, and that will make your output to switch from minus Vsat to plus Vsat. So this is the instant where I can say that output will switch like this, and then it will come to plus Vsat. Now till the next comparison, the next comparison will happen only at this point. So till that point, the output will be retained at this specific voltage till this point, because again when it reaches this point, what happens? Till this point, your plus Vsat, plus input, the non-inverting input terminal is having a higher voltage, so output will stay at plus Vsat. But again at this point, a comparison is made, and soon after that, your plus input terminal, the non-inverting input terminal is actually going lesser than the reference voltage. That will make your output also to switch from plus Vsat to minus Vsat. Right. So after this will be repeated in the next comparison. The next comparison will happen only at this specific point. Alright, so this is how we can write the output of a non-inverting comparator. Alright, I hope this is clear. So this comparator works based on one thing what we should know is this: your output will be gain times the difference voltage, and if the difference voltage is positive, it will go to plus Vsat. If the difference voltage is negative, it will go to minus Vsat, right? On the basis of that, we say that this is a non-inverting comparator or an inverting comparator. So if this is a non-inverting comparator, and if you want to have an inverting comparator, we can easily draw an inverting comparator by just exchanging the input voltage. This is minus, this is plus, or even you can retain the plus and minus. To the plus terminal, we can give a reference voltage. The reference voltage need not be always positive. A reference voltage can be anything, and the negative terminal, we are giving the signal voltage, V signal, and here we will have the output voltage. right? Now, even in yeah, so what will be the result of this? Here we have given input voltage to a negative input terminal, so the output will be, we can write that the output will be, how will I write the output expression? We can write V out equal to plus V sat. When will be plus V sat? When your V signal is less than, sorry, when your V signal is less than Vref, and minus V sat when your V signal is greater than Vref. On the basis of that, we call this as a, we call this as an inverting comparator. And in both non-inverting comparator as well as inverting comparator, you can try out by taking a reference voltage as positive or reference voltage as negative, and you can try getting the output of that, right? Now yeah, so we discussed both about inverting and non-inverting comparator with connecting a reference. Now another simple circuit what we can get is called as a zero crossing detector. Zero crossing detector. Right. So this is one of the important and the simplest application of the comparator, where we can actually convert a sine wave to a square wave. Very basic comparator. So the circuit is very simple. If you have a Opamp, what we can do is, say if you are connecting input signal to this point, say this is input signal, and if you are keeping the other point, the one of the input terminal ground, what can you expect at the output? So when you keep the other voltage as ground, the meaning is we are making the reference voltage V reference, we are making equal to 0. So the moment your reference voltage is equal to 0, what will happen at the output? Whenever the signal crosses 0, the op-amp will respond to that and will produce an output, right? Say this is your sine wave, right? Now this is a sine wave, which is your V signal, and now the reference voltage here, reference voltage is not any positive or negative voltage. The reference voltage is 0 axis itself. So when the reference is 0 axis, you look at this is the point where the comparison is made, and after, whenever the signal crosses this point, op-amp will make a decision. That will happen here, this point as well as this point, right? So what is the result of this? When in all these crossings, in all these 0 crossings, we will see that a decision is made by the comparator, and depending on whether the comparator is an inverting comparator or non-inverting comparator, you will have an output. What will be the output? Output will be switching between plus Vset and minus Vset accordingly, right? So this circuit where the reference is made as 0 is called as a zero crossing detector. All right, fine. Now so far what we discussed is about the very open loop configuration, open loop op-amp configurations and the applications, right? But now when you look at these kind of open loop applications, whether it is a inverting comparator, whether it is a non-inverting comparator, or in case of zero crossing detector, there are few challenges which made people to think and improve the circuit in order to overcome some of the limitations. So let us look at some few issues with these kind of comparators. So limitations or issues with open loop op-amp circuits, especially comparator. We are talking about comparators here, right? So now I consider input signal. Input signal can be of any frequency, right? That depends on the application where we use. In certain scenarios, in certain cases, the input signal can be a very slowly varying waveform, a very slowly changing waveform. Say for example, my input signal is a very low frequency signal, something like this, which is a very slowly varying waveform. And we do have a reference, say for example, we do have a reference voltage over there, right? Now, these kind of waveforms will take more time to cross zero. Say this is true in the case of zero crossing detector, especially what I'm trying to discuss now is with respect to zero crossing detector. Say for example, this is a zero voltage, right? Now you have an input signal here, and input signal will definitely take a long time to cross a zero, right? See, I have drawn a waveform which is fitting to the screen, but you can think about in scenarios where you have a very slowly changing input signal waveform, right? So in such cases, the input voltage will take more time actually to cross the 0 volt line, and therefore you will not see that the output voltage will be switching quickly from one saturation voltage to the another, because look at this point here, the switching will happen here, after that it will happen at this point, then at this point, and then in some other far point. So depending on the frequency of the signal, if it is a very slowly varying waveform, the switching will not happen immediately, right? But at the same time, if at all there is any presence of noise at the input terminals of Opamp, right? So we have an Opamp, and say there is plus and minus terminal. To one terminal we have connected a very slowly varying waveform. The other terminal, say it is kept grounded. Now this waveform is very slowly varying, but at the same time, if at all there is some noise affecting the input terminals, some noise voltage at the input terminal. So generally we know that when we say noise, the voltage in millivolt or microvolt range signal. Now such a input voltage, when such small input voltage come at the input of an Opamp which is open loop, see Opamp will definitely respond, right? Because we know that the output of the Opamp will be A times non-inverting voltage minus inverting voltage. Now the inverting voltage, say it is kept at 0, the non-inverting, the other signal is actually very slowly varying, it is not making making a change because of the slow variation. But say you have a varying noise signal present at that input terminal. So what will happen, depending on this noise signal, the noise will be at the input of the Opamp, right? So based on that, the Opamp will try to respond, and when the Opamp starts responding to this noise signal, what you can see will be when Opamp start responding, what will happen, the output will be actually driven to minus Vset, then again plus Vset, again minus Vset. So this will keep on changing, right? Because the noise at the input terminals will cause or output to fluctuate between the two saturation voltages, because noise is quickly varying, the input signal is actually very slowly varying, but the Opamp input terminal, it will not understand, right? Based on the signal variation at the input, this will operate, and based on that a decision is made and the output will be coming, right? So what you will see is there will be random fluctuations between the two saturation voltages, between plus Vset and minus Vset. So what is actually happening, it is actually detecting zero crossings even for the noise signals. Along with the input signal, it is actually detecting the zero crossings for the noise signals as well, right? So this is a potential problem, because what you will expect is your output will be keep on switching between plus Vset and minus Vset, making transitions, but it is not actually the intended transition, right? I hope you understand the scenario. There is a slow changing waveform where the Opamp is connected, one input terminal is connected, the other input terminal, say it is kept at 0. Now the comparison is made between 0 and this slowly varying input signal, but at the same time, if there is some noise signal coming at the input terminal, because the other is grounded, so if the noise terminal is coming to this input terminal, what will happen is, by taking this signal as a reference, or by taking the input signal as noise, Opamp will start responding, which may result in random fluctuations at the output, right? So this random fluctuations at the output will give you erroneous result, because what we need is the result or the response of the circuit whenever the original input signal crosses 0, but that will not happen here because of the noise, the presence of the noise signal. So this is one such case. So in these kind of situations, it is not advisable to use op-amp in open loop configuration, and the improvement on the circuit is actually to establish a regenerative mechanism, or to establish a positive feedback. So the remedy here is to establish positive feedback in the circuit, right? So why do we need this? Why do we say that it is a positive feedback is required? Because we want to make a decision, and the decision is the logic levels, or in this case it is switching between plus and minus V cell. The positive feedback mechanism also can give the same, but at the same time the positive feedback mechanism should eliminate the issue what we discussed now, right? So such a circuit is called as Schmitt trigger, which we will discuss in our next class, right? So Schmitt trigger is a circuit which is based on positive feedback mechanism, which can remove these kind of random fluctuations which can come at the output whenever there is a noise signal present. Alright, so that we will discuss in our next class. So if you have any questions based on today's discussion, you may please ask.